Traditionally, we've scaled relational databases by using vertical scaling, that is, by using a bigger machine with more power and memory. But vertical scaling is expensive and not very resilient. For Azure SQL databases, you can approach the problem differently and use a partitioning strategy Azure SQL calls sharding. Sharding distributes data across multiple Azure SQL databases. Each database has the same schema, but different records of data inside. As we just discussed, you could shard data across the databases using a range, like a range of dates or key values. And if you're building a multi-tenant application, a piece of software as a service, then a popular sharding key is to use a tenant ID. Each of your tenants receives a unique ID and therefore a unique database dedicated to holding the data for just that tenant. In this scenario, there's one database that is the shard map manager and contains all the metadata about how to reach the rest of the data in the shard set of databases. Notice these databases have different sizes on the screen. What I'm trying to show you is that not only are we scaling horizontally by adding more databases, we can also scale vertically with each database to give the database the right amount of resources to use. You could also place the databases into a SQL Elastic pool to assign resources. And Elastic is the key word here. Azure SQL provides Elastic tools to help you manage and work with shard sets. For example, an Elastic database job allows you to execute SQL commands against all the databases in the shard set. There's also an Elastic database query if you want to query data across the different databases. There's quite a bit to explore and learn about Elastic database tools and sharding with Azure SQL Server. I just want to make you aware of the possibilities and also again mention that nearly everything in Azure has a partitioning strategy. For example, Cosmos DB is very easy to partition. And this is just one specific example with Azure SQL. Well, let's move on and talk about some more application patterns you can use with data to achieve scalability. When working in large cloud systems and talking about data partitioning, you're eventually going to hear about the CAP theorem. I wanted to take some time to talk about the CAP theorem. The CAP theorem is very useful in thinking about and designing the qualities of a distributed system. There's many nuances to the CAP theorem, but what I want to give you is a general overview that will be useful for thinking about distributed systems. The C in CAP stands for consistency. A consistent system guarantees that every read operation will see the most recent data. Imagine a system where user A logs in to a social media account and updates their profile. In a consistent system, every other user will see the updated profile information the next time they read the profile, even if the read is just a few nanoseconds later in time. Perhaps the system is using a relational database and ACID transactions, where ACID stands for atomic, consistent, isolated, and durable. Using ACID transactions everywhere is one approach to building a consistent system. The A in CAP stands for availability. We could say that availability means every request receives a response. We can never achieve perfect availability, but if we design for availability using some of the techniques that we're looking at, we can achieve a system where, for example, 99.9% of the requests will receive a response. Just like with consistency, where we use database transactions to build consistency into the system, we have to design for high availability when the business demands high availability. Finally, the P in CAP stands for partition tolerance, meaning a request to the system will receive a response even when there are components inside the system that are not able to communicate normally. We just talked about data partitioning, and we know that partitions distribute work and distribute data across multiple nodes. But in the original CAP theorem, the P, the partition, is a network partition. That is a failure that splits the network and causes some parts of the system to be unavailable. So maybe nodes A and B can communicate, and C and D can communicate, but A and B cannot communicate with C and D because of a partition. Today, most people expand partition tolerance to include any type of failure that would take something offline. So not just a network failure, but also a server catching on fire or a server that is offline to apply security patches or software updates. The CAP theorem was put forth by a computer scientist named Eric Brewer, who stated that a distributed system can only have two of the three guarantees here. That is, a system cannot guarantee to be available, consistent, and partition tolerant all at the same time. Instead, in the design of a system, you need to find an intersection of two of these three qualities that you are most comfortable with. So the first intersection is the intersection of availability and consistency. This means every request will receive a response, and every response includes the latest data, like my latest profile information. However, without partition tolerance, there are parts of the system that might be degraded or unavailable, and during that time, I would not be allowed to update my profile information, or the system might need to wait for the partition to heal and a node to come back online before processing more requests, and waiting can hurt system performance. This intersection is a bit of an odd spot for cloud systems to achieve high availability without introducing redundancy, queuing, caching, and other techniques that impact consistency. As we'll talk about in just a bit, you can find articles that critique the CAP theorem and raise these types of points if you're interested. A more interesting intersection is the intersection of consistency and partition tolerance. This says that we want to maintain consistency, and we have partition tolerance, even if this means sacrificing availability. So if there is a partition, my system is going to stop being available and stop processing requests to make sure the system stays consistent. And finally, there's the intersection of availability and partition tolerance. We want our system to be highly available and resilient to failures, and we're willing to sacrifice consistency to get there. And it's not that we might give up consistency altogether. Many systems are eventually consistent. For example, if I update my profile on a social media site, maybe other users on other continents won't see my updates for seconds or minutes or maybe even hours, but the system will be eventually consistent and other users will eventually see my updates. This could happen, for example, because we designed the system to be available and partition tolerant by using geo-replication in our storage, like SQL Server geo-replication. When I write my updated profile, I'm not going to use distributed transactions to update databases around the world, because distributed transactions can be expensive and make the system unavailable during a partition. Instead, we allow our database to asynchronously replicate data around the world, and eventually the system will be consistent. But in the meantime, different pieces of the system can stay up and available. Obviously, your choices here depend on your business. Does your business value consistency, or does your business value availability? So a social media site might value availability. A stock trading application will probably value consistency. And that choice, though, doesn't impact the entire system. You can have pieces of the system that are AP and other pieces are CP, but you won't be able to build the entire system and make all three guarantees for availability, consistency, and partition tolerance. You have to choose which two of these features that you want. So with that in mind, let's start looking at different pieces of an architecture for a system that falls more into the AP category, which is favoring availability and partition tolerance. Partitioning is a common pattern to scale at the data persistence layers of your application. And then inside the application itself, there are many architectural patterns to scalability. For example, in previous modules, we've talked about an application that uses a data source like Cosmos DB or Server, but also uses architectural patterns like the command query responsibility segregation, where the abstractions and the code used to write to the database are separate and different from the code path used to read from the database. For read operations, for example, you could read data from a separate reporting database that is totally optimized for the data that the system needs. You could even pre-aggregate data inside the database. You could also read data from a cache, like a Redis cache. And this is what we will explore in more detail in just a few clips. Both these approaches could increase the performance and scalability of your application. For write operations, the system might not talk directly to a database, but instead send commands to a message queue. We saw a quick example of service bus queues in the last module when we talked about resiliency. Queues can not only help you build more resilient systems, because a queue can capture a message even when other backend systems are being updated, but queues can also help the scalability of an application by load leveling and smoothing out the traffic spikes in the system. We keep the front end of the application responsive by not waiting for long-running operations to complete, and we never overwhelm the capacity of the backend system. This is a scenario, again, where you can think about the CAP theorem. With all this queuing and caching and partitioning, what is the impact on my user who is trying to publish data for other users to see? With these sorts of designs where there's caching and queuing and partitioning and asynchronous operations, we are favoring availability and partition tolerance over consistency. When my user saves data in an operation and that operation is routed through a queue, there's a period of time where the system is not yet consistent. It's going to be eventually consistent, and those write operations are going to show up, but perhaps not immediately when other users are refreshing the system. Now, since we've already seen service bus queues in operation, let's turn our attention to caching. In this architecture diagram that we've looked at earlier, I placed a cache between the application and the database. Caching can be useful for a number of scenarios. Caching can improve both my performance and my scalability. It's usually faster to retrieve data from a cache than it is to go all the way to the database, execute a query, and wait for the data to be put together again. Caching can also help with high availability and partition tolerance, because even if the database is unavailable, if I have a copy in a cache, I have a second read-only source of data to work with. Of course, caching does add some complexity to the system. You have a bit more code, you have a bit more work to do when debugging a data issue, and caching can take away from your consistency guarantee if you allow users to read stale data. You also have to figure out an effective cache strategy, how often to cache, when to cache, and when to invalidate cache entries. These are not always trivial problems. In this module, we're going to look at Azure Redis Cache. Redis is an open source cache service that you can use from multiple application instances. So you can think of it as an in-memory distributed database. So reads and writes are extremely fast. You can also replicate and cluster Redis for high availability. Let's take a look. Let's explore how to use Redis Cache from a web application by first creating a Redis cache. So I want to do a search for Redis. The first result in this list is the resource that I want to create, Redis Cache from Microsoft. So I'll click that entry. Scan through the descriptive text and then click the Create button. And of course, the first thing I'll need to do is provide a name. Let's call this PS Redis. I do want this to be in the Pluralsight subscription. I could place this into an existing resource group with my web application. Create a new resource group called PS Redis. And ideally, this Redis cache would live in the same location as the web application that's going to consume this Redis cache or use this Redis cache. So I'll use the East US location. And then comes the pricing tier. We can click here to view the full pricing tiers. For this simple example, I'll be able to go with just a basic pricing tier. That gives me 250 megabytes of cache. But if I wanted to use some of the more advanced features that we're not going to use in this demo, I could select a premium or a standard caching plan. And some of the features that are available in these higher plans include clustering as well as sharding. So once again, we're coming across that idea of partitioning. What happens when I have so much data to cache that I cannot fit that data inside of a single Redis instance? That's when I could shard my data or partition it across multiple instances. If I'm caching social media profiles, for example, perhaps two partitions would be enough. One partition for all users whose last name starts with A through M, and another partition or shard for N through Z. But again, we're going to be able to get away with just a basic configuration here. And this is all the configuration that I need to provide. I'm going to create my Redis cache. This will take just a few moments, so we'll back when that's complete. Just a few moments later, and our Redis cache is ready to go. On the overview page for that resource, like every overview page, there's some action buttons, some important information, and some basic metrics. I can see load or memory usage on my Redis instance. I'm going to just add an application and show you two different ways to interact with Redis cache. One approach is going to be using a lower level Redis API that you could use from any .NET application, but I also want to show you an easy and native way to work with Redis from ASP.NET Core. Let's look at the Redis approach first. All we simply want to do in both demos is read a value from the Redis cache. And here on this page, I can see the entry is currently empty, but I also want to be able to type in a greeting, click this button, and set something in the cache that when I come back to this page, will display as the current greeting. Let's go to the code inside of Visual Studio. Here I have a Razor page that will respond to a GET request. This is where we will read the greeting from the cache, populate that into the greeting property, and it will display in the UI. And then here's a simple form that will post a greeting value back to that Razor page. When we post the greeting, We will use ASP.NET Core model binding to place that into the greeting property, and we want to set the greeting in cache. So first, let's read the greeting. Or first, let's establish a connection to our Redis cache. To do that, I'm going to create a field of type iDatabase. This is in the namespace stackexchange.redis, which is also the name of the NuGet package, which I have already installed in this project to speed things along. So stackexchange.redis provides a nice C# and .NET API wrapper for Redis that we can use from any .NET application. And I will call this private field when this page is constructed field. Now, of course, in ASP.NET Core, you can do this through dependency injection, simplify things, and inline some code here. Before I can reach the database, I will first connect, and I can do that by going to a class, the connection multiplexer, and asking it to connect. The multiplexer either needs configuration options or a connection string. And typically, information inside of your app settings.json file. Again, just to speed things along a little bit, I'm going to hard code the connection string into this razor page. Where do I get the connection string? Let's come back to the portal. Because inside of the portal, one place I could get to the connection string is through the access keys settings. And I can also get to this access keys right here from the overview layout. So I'm going to click show access keys. Just like that, storage and any other Azure resources that we've asked, there's two access keys available. And the portal also makes two connection strings available. These connection strings are designed to explicitly work with the stackexchange.redis NuGet package. So I want to click copy one of these connection strings, come back to the Visual Studio. I'll just paste this information in here instead of adding into app settings. And then I can pass my connection string into the connect method. Once I have this connection, I can then say that my database must have an NIS connection to get the database. I'm not associated with the connection. You can see there's a lot of other low-level APIs that allow you to manage your Redis instance. But I just want to get to the database. Once I have a database instance, things are very simple. Like making caches, Redis is a simple key value store. So when I take information into cache, I have to supply a key value that will identify that information. And then when I read the cache, I simply use that key to retrieve the information. So I could say that reading is what happens when I go to Redis. And I ask the value by a key. You can see there's a large API here that allows you to do things with geoposition, georadius. But what I want to do is a simple string get. And all I have to do here is provide the key information of some unique string that will identify the information that we get. And let's just use the name of reading. So the key value will be reading. When I want to set this reading, there is also a Redis string set. With this method, I can pass in a key and a value. So the key, and let's use reading, and the value will be the string value that is in that property that's typed into the form. And yes, of course, there's overloads that allow you to specify things like an expiration for this cache entry. But let me go ahead and save this file, come back out to our web browser, and give this a try. I'm going to refresh the page. I can see there is no current greeting, but if I want the current greeting to be hello with an exclamation point, when I come back to this page, indeed, I can see hello with an exclamation point. I can also verify that this entry is in my Redis cache using this handy console. On the overview blade, there's an action button console. When I open this up, this connects to my Redis instance. And there's over 100 different commands that I can issue to Redis to do some debugging and manage client connections. What I want to do is simply get a key. Let's see if we can get something for greeting. And I do, in fact, see that greeting come back. So what we've looked at so far is a lower level Redis API that I can use that application to interact with a Redis instance. Now let me show you a slightly different approach that I can use from ASP.NET Core. This setup is exactly the same. The Razor page is exactly the same. We're going to display a message this time instead of a greeting. We're going to have a form where a user can input and save the message into the cache. And we have a Razor page model that accepts GET and POST requests. But this time, instead of simply connecting to my Redis instance, I'm going to create a constructor that will take a parameter of type I distribute to cache. This is in the namespace Microsoft extension caching.distributed. We'll call this cache. I'll use full period to say initialize my private field to hold this cache. And what I'm going to be able to do is configure my application to use Redis as a backing support for this distributed cache. But throughout my ASP.NET Core application, I'm not going to work directly with Redis API. I'm going to work with a distributed cache. And this gives me flexibility and loose coupling. When I'm in development, for example, I can configure an memory distributed cache. But I'm doing development, I don't have to worry about setting up a Redis instance. When I'm doing production, we'll see how I can just start up CS a little bit, but switch over to point my distributed cache to Redis. When I want to read my message, it's very simple. I can say message equals cache, and when I want to get a string, again, a key value, let's use unique message. When the user is giving me a message to save, I can use cache.setString, pass in my key, which is the same as message, pass in my value, which is the message itself, and the value will place cache. Now, I'm not only caching simple string values, but of course, those string values could contain JSON data, they could contain XML data. There's a lot of flexibility in what you store inside of the cache. There's also, with the distributed cache interface, distributed cache tree options, where I can specify things like an expiration. And then the only bit of code that I need to add to make my distributed cache work with Redis is to come into startup.cs. And inside of your services, where I set up a container, ASP.NET Core dependency injection, and add all the services for the MC framework and for the MC framework and so forth, I'm going to add a distributed Redis cache, which I should point out is available through the NuGet package, which is microsoft.extensions.caching.redis. And in fact, that NuGet package relies on stackexchange.redis. But with this method, I can specify options. And what I want to specify is options.configuration. And this is where I can place my connection string. I still have the connection string that I copied from the portal into my clipboard, so I'm going to paste that in. And with those changes in place, I should be able to save the application to the browser. Let's go and now look at the cache demo. The current message is empty, but let's use hello Redis and set this message. And I can now read that message out of the cache too. So a Redis cache can be very easy to use and provide a lot of benefits in terms of both performance and scalability. The more cache data that I can use, that's less time that I have to spend sending queries to my database. And by having a distributed cache, so a cache instance that let's say all my app service instances use, I don't have to worry about spinning up a new instance of my app service and having that instance be a little bit slow because there's not a cache that's available. The distributed cache is already there and warmed up and populated with entries. Another place where we can take advantage of caching is on the front side of the application, in the Content Delivery Network, or the CDN portion of the CDN is a place where I can host my content like images, CSS files, JS files, HTML templates, videos, pictures, and any other file I would otherwise serve publicly from the file system of my web server, and generally content that doesn't change frequently. A CDN will cache my content on low latency and high bandwidth connections all around the world. Not only does a CDN benefit my customers then because content arrives faster, it can also help the performance and scalability of the application itself because the application has fewer requests to manage. Instead, the CDN handles some of the requests. The Azure CDN is easy to use and includes support for SSL and custom domains. You can cache public content from your app services, from blob storage, or any web location. Let's take a look. For this part of the demo, I've added an image page to the application, and this page will display the same image twice. It's a very large image. It's about a 7 megabyte JPEG file. And what I'd like to do is offload this image from my app service to a content delivery network. And by the end of the module, we will serve one version of the image from the app service, and we'll serve the second image from the content delivery network, and we'll be able to look at the developer tools and see if we've saved any amount of time doing that. We'll also see how easy it is to use the content delivery network. In order for it to work, I need to come into Azure, and I need to create what's known as a CDN profile. So I'm going to search for CDN, and the first result that comes up should be CDN from Microsoft. I'll click to select this, and then click Create. And what I'm going to do is set up a profile that allows me to work with one or more endpoints. Each endpoint will be associated with a specific web application, and these web applications could be deployed in app services, they could be deployed to virtual machines, they could exist in another cloud provider or in my own data center. We'll see how easy it is to set up endpoints here in just a second, but I do need to give my profile a name, so let's call this PS-CDN. We can imagine we're setting up the CDN profile for a number of applications that we manage, in which case I would put it in the Pluralsight subscription. I would probably put this in a new dedicated resource group. I'll leave the location as East US, where the metadata for this resource group will live, because the content delivery network itself is a global resource. And now I need to select a pricing tier. There's currently 4 options for the pricing tier. You can click this hyperlink to view more details about each pricing tier. There's offers from Verizon, Akamai, and Microsoft. And each of these options, they'll offer the same features, that is, the ability to cache content from all around the world. But there are some differences in the feature set. For example, this premium pricing tier will give me advanced analytics about how the CDN is behaving. I'm going to go with the standard Microsoft tier, which is currently in preview, but it does allow me to work over HTTP and HTTPS. I can set up custom domains. There's compression and geo-filtering and a number of other features, but let's go ahead and create this. I'm going to do the CDN endpoint later. Creating a CDN profile is generally a pretty quick operation, so I'm going to come right back into resource groups for PS. Maybe refresh here once, and here is my new CDN profile. At this point, I'm up an endpoint. So remember, an endpoint is going to be associated with a specific web application. So if I want to serve assets for my PS traffic application, I'll need to set up an endpoint that maps to that PS traffic application. I can do that by clicking on the Add Endpoint action button up here at the top. And the first thing I'll need to do is give my endpoint a name. Let's call it PS traffic. Notice this forms the URL ps-traffic.azureedge.net. So here's how all these CDNs work. If I make a request to ps-traffic.azureedge.net/images/picture.jpg, the first time I make that request, the content delivery network will not have that image available. So what it's going to do is turn around to the origin that I'm about to specify, which will be my app service, and retrieve that picture using the same relative path. In other words, coming over into Visual Studio, this is the Razor page that is displaying that JPEG file. The first image, we will continue to serve it from the local app service file system. So this image lives in www.root images and there's hike.jpg. But for the second image, I'm going to use the same relative path /images/hike.jpg. But I'm going to use the name of my new CDN endpoint, which is ps-traffic.azureedge.net. So I can say, let's serve this from ps-traffic.azureedge.net. When the content delivery network receives this request, it turns around and makes a request to my app service for /images/hike.jpg, retrieves that picture, and then will cache that picture for up to 7 days. This is why it's important to generally only use static content that is not going to change frequently. Yes, there is the ability to go out and purge the content that is already cached in a CDN, but many times your images, your movies, your banners, those types of assets are not going to change frequently. In order for the CDN to turn around and make that request to retrieve my content, I have to specify the origin host name, but first the origin type. So I can select an origin type of storage. For that scenario, what Azure CDN will do is turn around and go to my storage account into a blob storage container that I specify and load all of the content that it needs from that location. This is a great option to use if you build and release process that can take all of the static assets that you want in the CDN and push them out to blob storage. I'm going to do something simpler, which is simply to allow the content delivery network to come to my app service to retrieve the content. Now, generally, for that scenario, what I would do is select web app, because web app means app service. And once you select web app, under origin host name, this will produce a dropdown that will list the app services that are in your subscription. However, we have a slightly special situation here. Earlier in the course, we deployed 2 different app services, one in East US and one in West EU. Those are the 2 entries that are here. And then we created a traffic manager profile that distributes traffic across these 2 app services. Currently, the CDN traffic Manager profile don't play well together if you select Web App, so what I'm going to select instead is Custom Origin. Custom Origin is also what you could use if you have your web application hosted on a VM or on some other web server that's in your own data center or another cloud. And what I need to tell the CDN to do is now where to go to retrieve the original content. You might remember our Traffic Manager profile looked like ps-traffic.trafficmanager.net. I just want to copy that URL so I don't make a typo and paste that in here and remove the HTTP portion. That is my origin host name. Down here, if a request arrives over HTTP, I will allow that. The CDN will then retrieve the content over HTTP. I'm also going to allow secure HTTP. I don't want to set an origin path. With an origin path, the CDN would go to a different path to try to retrieve the content from the underlying web application. I just want the request to map directly. So requesting /images/picture.jpg from the CDN will turn around and request /images/picture from my original app. I'll leave the host header here that will be passed along in the request that the CDN makes. I will leave this optimized for web delivery, and I'm going to click Add. At this point, I can come back and redeploy my application, and I'm also going to need to wait for up to 10 minutes for these changes to propagate throughout the content delivery network and for all the settings to be updated. So I can do the deployment, grab some coffee, we'll come right back. Some amount of time later, and I can refresh my redeployed application. The image is still appearing twice on this page, but this second instance of the image should be coming from the CDN. So let's take a look at what happens during from the developer tools in Chrome. So with the browser cache disabled, press on the refresh button again. What I can see is that the first image that is served from ps-trafficmanager.net, so directly from my app service, that loads in about 1.42 seconds. Meanwhile, the version of the image that is served from ps-traffic.azureedge.net, this one's being delivered in 872 milliseconds. That's roughly 40% faster. Of course, you'll want to do some benchmarking and testing to see how the CDN performs with your application and your assets. But just remember, not only is the CDN delivering content faster, it's also automating requests that would take to your application. Another Azure resource that you might consider adding in front of your system, particularly a system that provides APIs to outside developers, is the Azure API Gateway. The API Gateway allows you to organize and publish your APIs, both public and protected, to developers, partners, and customers. If you want to charge money for the use of your API, then the API Gateway will provide most of the infrastructure and monitoring that you need. From a scalability perspective, the gateway also allows you to add cross-cutting concerns like rate limit throttling so a specific customer doesn't abuse your API. You can also add response caching in the gateway to tune the application performance without redeploying an API. Think of the gateway as a proxy or as a layer of indirection between your customers and the operations across all of your APIs. The gateway provides an area where you can publish, manage, and monitor your APIs, and a portal where clients can log in, create access keys, raise issues, and view the documentation for your APIs. Let's give this a look. Before we can use the API Gateway, it would be nice to have an API to manage. So in our demo application, I've added a new controller to provide an API for reading and creating course-related information. The model that you see here on the screen could represent a Pluralsight course. We're only going to hold the title and the link and also have some sort of primary ID to identify a specific course. But here in the API folder of the project, I have created a courses controller. This controller will respond to the route /API/courses. And there are API endpoints inside this controller to respond and retrieve all the courses that are available from some course data source, as well as retrieve a specific course if you pass in an ID, so /API/course and the identifier. And there are also endpoints where you can post to create a course, put to update a course, and delete to remove a course. All of these API actions, I want to point out, use some additional attributes that provide metadata about the different types of responses that this endpoint will provide. For example, if you ask for a specific course by ID, you might have a 200 OK response, in which case you'll receive the course data, or you might have a 404 not found response. It all depends if that course was found inside of the data source or not. And I'm using ASP.NET Core 2.1, where I can use action result of T to have a better description of the model that's being returned by this endpoint. All of this is important because these attributes and these return types like action result of T will help me produce documentation that I can import into the API gateway. And this will in turn not only make it easier for me to manage my API, but also make it easier for me to give my API to external customers and partners. I can provide the documentation that is generated by this metadata. Now, I've already deployed this version of the application into the app service that we've created earlier, or rather both app services that have Traffic Manager in front. And so if I come to the application and go to /API/courses, what I should see is a JSON representation of all the courses that exist in the current database. But what I want this application to have is not only these endpoints that you can interact with to read courses and create courses, but I also want to provide a description of each of these operations, something that would describe the shape of data and the types of responses, something that will read the attributes and the metadata about my controller and produce that documentation automatically, including even which HTTP verb is used to invoke a specific endpoint, get or post. In the world of web APIs these days, there are a few different metadata formats that I can use to describe my API in a way that other developers and other tools can understand that documentation. First, there's WSDL, the Web Services Description Language, which was very popular during the WS XML days. There's also WADL, short for Web Application Description Language. And then there's a format known as Swagger, or OpenAPI. Swagger was designed explicitly to support modern HTTP-based APIs that use JSON. And I want to add Swagger documentation to my API. With ASP.NET Core, all I need is a single NuGet package and some configuration, and my application can then generate most of the documentation itself just using metadata that is in the application. .NET metadata like the type and the name of parameters to a method, the data annotation attribute, XML comments if I add XML comments to my source code. It's not something that is required to use Azure API. It's going to make my life easier because I will have all the information that I need to describe my API, and I don't have to do that by hand. The NuGet package that I added to this project to help me with this is a NuGet package named swashbuckle.ASP.NET Core. Once you've installed this package into a .NET, add some configuration to the application. .NET Core, of course, this configuration to the startup file. So first, let's take a look at configure services. And inside this method where I configure the container for ASP.NET Core, you can see I've added a call to add Swagger Gen. This will add the Swagger generator as a service. And the Swagger generator is a component that knows how to look at the application model made up from the .NET Core metadata in this project and produce a Swagger document which describes my API. Specifically, we're going to add a Swagger document with the name courses-v1. And that name is important because it will appear and I will tell you there's a lot of flexibility and customization that you can add with Swashbuckle for Swagger. You can control nearly every part of the generation process. We're going to take defaults, but the ultimate goal of this generation process is to produce Swagger, which is in JSON format, and I want to be able to serve that Swagger document over HTTP to anyone who wants to see a description of my operations. And because I want to serve that document up, that also means I need some middleware configuration that will process an HTTP request that is asking for this Swagger document. So if I scroll down into the configure method where we configure our middleware, I've added two pieces of middleware here. First, app.useSwagger. By default, this will listen to a request for /swagger/ the document name that we just configured in services /swagger.json. So for our application, /swagger/ courses-v1 swagger.json will give me the document that describes the API inside of this project. You can actually see that string here in the second piece about in just a second. For right now, let me keep that relative URL. Let me come back to the browser where my application is running. Let me paste this in. So it's ps-traffic.trafficmanager.net/swagger/courses v1/swagger.json. And what I'm seeing is a JSON document that describes my API. I can feed this document to a tool that understands Swagger. And there's various tools that can work with this information to do different things like generate code. The other piece of middleware that I've added with app.useSwaggerUI is a piece of middleware that will provide a friendly user interface to describe the API that is based on that document that we just saw. This Swagger UI middleware will listen to a request for /Swagger by default. And since I've already deployed into Azure, let me come back and go to just /Swagger. And I'm now going to see a friendly description of all the APIs that are available inside of this application. This is a direct link to the Swagger file itself. Here's the different operations that are available on my controller. For example, I can get all courses. Notice this documentation can tell me that this will return an array of data where each object in that array will have ID, title, and length properties. It will also tell me that I can post to /API/courses. And what I need to post is a model that includes ID, title, and length. Length is going to be specified as an integer with minimum and maximum values. That came from data annotations that are on my model. So specifically in .NET, the range attribute and the required attribute. You might have noticed them when I showed you the model before. And the types of responses that I expect to receive will be HTTP status code 201, which is successfully created, or perhaps an HTTP status code of 400 for a bad request if I send along, for example, a data structure that didn't include the required title. I can even try these operations out here using the try it out button. If there were any parameters required, I can enter them here, but I'm just going to click execute. This will even give me curl command line syntax if I wanted to place this into a script. But down here, I can see I did receive a response, a 200 status response, and here's the data that's coming back from that particular endpoint. It happened automatically, and if I update my controller to change little things like parameter names or add data annotations, all I would need to do is redeploy and the documentation would automatically be updated for me. Again, none of this metadata is required for using the API gateway. But as I mentioned earlier, this is going to make life easier because I can use this metadata to describe my APIs to Azure API Gateway instead of creating information by hand. So with the API in place and some metadata in place, let's next look at creating the gateway. Inside the portal, let's do a search for API management. What I should be able to find is API management from Microsoft. This is what I want to create. And as usual, the first bit of configuration is to enter a name. Let's try PSAPI or PSAPI2. It does have to be unique in the Azure-API.net namespace. And this URL, psapi2.azure-api.net, this is the URL to my API gateway. Instead of other developers and customers and partners invoking the API on my PS Traffic website, I'm instead going to give them this URL, and this is where they're going to send their web service calls. This API gateway, API2, will accept that API call and then route the call to the backend, which is on PS Traffic. Along the way, it can verify API keys and JOT tokens and certificates. It can enforce usage quotas and rate limits. I can add course headers. This gateway is a proxy that sits in between the client and the implementation of my API. And because it's a proxy sitting in the middle, there's all sorts of magic that this API gateway can perform. I won't have time to show you all these features. This is going to be a very quick introduction, but I do want to create this API management service in the Pluralsight subscription. I'm going to create a new resource group. Let's also call that PS API2. The location will be East US. I'll just enter an organization name of Pluralsight and use my administrator email, scott@odecode.com. Now we come to the pricing tier. You can view the full pricing details by clicking on this hyperlink. The different tiers offer different SLAs, from no SLA for the cheap developer tier, up to 3.5 nines for the premium tier. And each tier will have slightly different features. For example, the amount of cache that is provided, how far you can scale this, and of course the all-important requests per second. Since we're just taking a look at API management for, let me select the development tier, click select. I'm going to click create, and we'll the API management service is provisioned and ready to go. Just a short bit of time later, and my API management service is set up, and I'm on the overview blade where you can see important details about the management service, including the gateway URL. That's the base URL that clients are going to use to contact the APIs that I have implemented elsewhere. And I have some high-level metrics on this page that will show me how the gateway is being utilized. Over here on the left, you'll see common settings groupings for setting up notifications, managing certificates and security, scaling, and of course I can also apply a custom domain instead of using the gateway URL. For a real business management service, I would have a domain and my own SSL certificate. There's metrics, I can hook up application insights to my gateway, and I'm going to show you some of the core features and concepts of the management service. First, the idea of APIs, products, and subscriptions. APIs is where I manage my collection of APIs. So I can add not only the Pluralsight courses API to API service, but I can also add other APIs for the service proxy, including APIs that are hosted in Azure Functions, or on a virtual machine, or in my own data center. So Pluralsight courses will be just one API, but one of the ideas behind this management service is that you can manage an entire collection of APIs. The way the APIs are surfaced to clients and customers and partners is by placing the APIs into a product. It is a product that my clients will register for and subscribe to gain access to the APIs. One or more products depending on what capabilities and behavior the client see. In fact, if I go ahead and click on products, I will see products, a starter product, and an unlimited product. The difference between these two, as we'll see a little bit later on, is that if someone signs up and subscribes to the starter product, they will be restricted in the number of requests per minute that they can make to these APIs. So if I was charging for a subscription, the starter subscription might be free or a very low cost compared to the unlimited subscription, where there is no rate throttling, so a subscriber to this product can make an unlimited number of calls. These subscriptions themselves I can manage in the subscriptions area, but I do want to come back to the overview and click on this top-level action button, Developer Portal. That's going to open in a new tab in the browser. This Developer Portal is where I can send my customers and clients that want to use products and APIs, because it's from here where they will be allowed to sign up to use one of my products. It's also here where they can browse documentation for my APIs. You can see there's a sign up button here, but I am logged in as an administrator for this developer portal. That's why I have an edit icon over here on the left where I can change templates and styles to make the portal look different and customize the portal. If I click on this administrator dropdown, I can go to my profile, and it's from here, since I'm already signed in, and because I'm an administrator, I'm already registered for all the possible products here. This is where I can view my subscription details. So this is my subscription to the starter product. This is my subscription to the unlimited product. Here I can see my access keys and regenerate my access keys. And again, if I want to make an API available to clients, I need to place the API into one of these products. And I'll be able to view the APIs through the APIs link up here at the top. To get started with the management service, when I create the management service in the portal, there will be a very basic Echo API that is already registered and added to the two different products. And this is what your end users could see. They could browse the documentation for this particular API, see the request URL, look at the request headers that are required. And our goal for right now is to get the Pluralsight Courses API added so that it will appear under APIs and be registered with products. And end users would be able to see what are the available responses, the shape of the data that I need to send to this API. These are all I can maintain by coming to the APIs section under API management. So currently what we're going to see is that the only available API over here on the left-hand side is the Echo API. From here, I could clone this API or delete this API. What I want to do is add an API, and I can do that using the badges that we see over here on the right. If I had an API that did not have any Swagger documentation or open API documentation, there's no Waddle or WSDL, I could create an empty API and fill out all the details by hand. But because Pluralsight Courses comes with a Swagger document, aka an open API specification, I'm going to click on this badge, which will open a dialog, and I can import the API specification. I can do that by uploading a file or by coming to my Swagger UI and open up my swagger.json file. I'm going to do this, bring it back to the portal, paste it in. Once I move the focus off of that input, behind the scenes, Azure is going to go out and read my Swagger file. You can see it's already populated my display name and my name. I can add here a description. I can say I would allow this over both HTTP and HTTPS. I would caution you against using non-secure HTTP because clients will send confidential information in the HTTP, specifically a safe subscription will give them access to the base URL that my clients would use to reach this particular API, the URL for my API management gateway, API2.azure-api.net. And I'm going to go ahead and place this into the available product so that this API will be available for consumption. I'm going to go ahead and create this API. It'll take just a moment, and it's just here on the left-hand side of the screen, just below the Echo API. And if I click on Pluralsight Courses, I now have the ability to browse the specific actions that are available in that API. So the ability to get a course by ID, the ability to get all courses. This was demonstrating some power of the API service. We're going to explore some of these settings in the next clip. This is where I can add my policies or my rules on how the API management service should process arriving for this API. So there's inbound processing and outbound processing and backend and front end. This is where I have the ability to add caching or the ability to throttle the number of requests per second or per minute. I can also do things like add port headers if the original API doesn't provide cross-border reach. Now there's one more setting I need to put in place, and that's going to be this web service URL. Have that URL in your Open API specification so you don't have to come in here and fill this out later. But the basic idea here is that I've now described an API to the management service. And what I can provide here is the URL where this API is implemented. In other words, over here in my other browser window, I want to tell API Manager that my web service URL is ps-traffic.trafficmanager.net. So now whenever for the courses API, the API management service knows where to go to invoke the implementation for the API. Let me click Save. And then as soon as this is finished, we'll come over to the test tab. This again is where I can interact with the API, get all the courses. I'm going to click on up here is where I can add any parameters required. Here are the HTTP headers that are going to be sent along. There's a header here to disable caching for this test, a header here to enable request tracing, and here is the subscription key that needs to be passed along to give me access to this API. If you've used soft APIs that are packaged as services, like cognitive services, you've probably seen this header before, OCP-APIM-subscription key. In this header, I'm going to pass along my primary subscription key for the starter product. This request will go to ps-azure-api.net. So when I send this request, it means the API management service will turn around the request and endpoint, which will do the magic DNS to one of the two implementations of my API, which are deployed into app services. And I will get back the response, which includes the 3 courses that I've seeded the application with. So we're just scratching the surface of what we can do with an API management service. I do want to show you in a little more detail what I can do with policies in the next clip. This API gateway that we've created It has the ability to modify incoming requests to my API, as well as modify the outgoing response from my API, and perform any number of cross-cutting concerns at the API level, individual operation level, or even at a product. So, for example, if we come back into APIs and come to the Pluralsight Courses API, what I can see when I have all operations selected are inbound and outbound processing rules. If I click to modify inbound processing rules, what I'm doing here is applying a policy that will apply to all operations. And a policy could be something like add caching or add additional headers. I can even, for special circumstances, set up mocking. What this would do is tell the management service not to call the backend API, but instead just send back some static responses that I define. I can also come into the code view and see that these policies are specified in XML. Here on the left-hand side, I can see policies that apply to all operations for inbound and outbound. And on the right-hand side, policies that I can use. For example, in the outbound case, if I want to add CORS headers to the response, click to add this policy, and after I do some reformatting, around the settings for allowed origins and allowed methods and headers and so forth. I'm going to discard this and just point out that I could also apply this operation inside of the API. I can also modify the front-end description of this API. So if I wanted to include some additional responses or change the data shapes that are involved in the response, I can do that here. I can also modify the settings. So currently we have the management service set up so that an incoming would be forwarded to ps-traffic.trafficmanager.net. I could override that for this particular operation, send it to a different backend, and I can also authenticate calls from the gateway to my backend API. I might do that with client certificates. What it would allow me to do is have my backend API exposed on a public IP address. Require client-side certificates, I could shut the API off from the outside world, allow only the gateway call API, and enforce different authorization and identity rules in the API management service itself. These policies can also be applied at the So if we come back out and go to our list of starter product, and over here on the left-hand side, I can see policies that apply to this product. Again, an XML file, and you can picture these as being hierarchical. So if I apply an inbound policy at the product level, that policy will apply to all the APIs that are in this product. And you can see the policy here, a rate limiting policy. This is how we say that someone who is subscribed to the starter product and using a starter product subscription key is limited to 5 calls over a period of 60 seconds. There's a large number of pre-built policies that I haven't shown here, policies that would allow you to transform JSON into XML for the backend. I can also list IP addresses, and there's even the ability to C# code inside of these policies that will be evaluated at runtime and compiled by Roslyn. So the API management service can really be a resource if you want to build scalable APIs for the world to consume and be able to manage and monetize those APIs. In this module, we looked at Azure features and patterns that we can use to build more scalable applications. From data partitioning in our data sources, like sharding in SQL Server, to caching with Redis and the CDN service, to the API gateway, there are many resources that we can take advantage of in Azure for scalability, not to mention some of the features that we covered in the Getting Started course, features like the auto-scaling features of Azure App Services. However, one of the most important requirements for building a scalable application is to understand how your application will perform under load before the actual customer load arrives. We'll talk about this next, load testing.